one. And maybe what we'll do on Tuesday, I'll probably make it do either Tuesday or Wednesday here. And then on Tuesday, I think what I'll do is go over it in class with you. Maybe this will be, I'll go over the solutions, even though I'll change the due date, I'll extend the due date to probably here, let's see, Tuesday's the 25th, probably the 25th or the 26th. So I'll change this and give you a couple more days. And then on Tuesday, we'll go ahead and talk about it. So let's go ahead and look at it again. I did show it to you on Tuesday. Okay. And let me just talk about these problems in generalities. And these are all concepts that are talked about in the first section of your textbook here. Okay. Chapter 1 goes into great detail on sampling. Okay. Now, we've talked about data, and what in your discussion, you probably treated the data in one of the following two ways: as a population. For example, the census looks at practically every citizen in the country. So they're looking at all of the data, which is a very, very large data set, but according to law, they have to query each individual in the country. So they're looking at a very, very large population of over 330 million. That's a huge undertaking, but that's their mandate, to look at all of the data that exists. In most cases, your discussion probably centered on a sample, a subset of that data. And a subset of that data has a certain numerical size. For example, somebody in California might take the census data and look for economic variables. When I filled it out, I thought I remembered some of the data that they were collecting, and some of it was economic, some of it was demographic, and so on. So someone in California might select some data from that entire population that the census collects and studies maybe trends in California, right? So they would be taking what we would call a sample of the data, some subset of the entire population. Okay? So in this problem here, we're talking about a fitness center. And what the fitness center is going to do is take a sample of data to try and understand what the frequency of the usage of the fitness center that the clients are using. They're using the fitness center possibly on a weekly basis. Some people go 2 to 3 times. And so what they'd like to do is sample their data, maybe over a period of a week or so, to see what the traffic is in a week or so. So the population in this problem would be all of the clients. Some of you belong to fitness centers and have been going to the fitness center. Many of them are closed now, unfortunately, but before the pandemic, you know, many of us visited the fitness center on a weekly basis. So the population is all of the clients, isn't it? There might be 1,000 members in the center, and what what is going to be done here is to collect data which would be the average or the mean amount of time that the clients in that sample spend visiting the gym on a weekly basis, okay? So the population would be all of the clients, the sample would be those clients that are selected. And what is the sampling procedure? Well, probably the observer who's collecting the data would set up an observation point, maybe at the front desk, where she sees people entering and exiting. And typically, there's a record of the entrance and the exit might be, she could query the individual as they leave and maybe ask them to give her an estimate of the time that they spend in the gym. She may ask for their name and then cross-check their name with their admission. The admission is usually a scan, a card with a scan code on it. So they might be able to identify the client as they're leaving and then ask them to give her an estimate of the time that they spend in the gym. Now, the average amount of time or the mean amount of time for the sample, and what she might do is collect some number of samples each day as people enter and leave the fitness center. And over the week, she'll have an accumulation of observations, which are simply times, the amount of time that the client spends in the fitness center. And with those data, she can calculate what we call a sample mean. I did mention the sample mean on Tuesday, and when we come to the second problem here, we'll talk more about the sample mean. So she might use the average amount of time as her statistic to estimate the parameter. The parameter would be the average amount of time or the mean amount of time for the entire population. But as I just mentioned, it's really not physically feasible for us in every case to have at our disposal the population of data. Nevertheless, we do define a mean for the population, and we call that the parameter, all right? So the parameter is the population mean amount of time. The statistic would be her estimate of this population parameter, and we would call that the sample mean. And we would denote that sample mean by this notation here, X bar. And I'll define it for you. It's just the sum of all the times, okay, divided by the size of her sample, that is the number of observations that she actually has collected over that week that she's observing the clients as they leave the fitness center. Okay, the variable is simply the amount of time. She might convert the time to minutes, and if someone is there an hour, her data value, her variable would be 60. If someone is there for 25 minutes, her observation is 25, and so on, okay? And I've just given you some examples of the data. So that's what you'll read when you read chapter 1. You'll read about different populations, subsets, or samples from those populations. And the important thing in this problem is to remember that a parameter is the variable for the entire population, and the statistic is based on the sample. Okay? And if we denote the variable by, let's say, an unknown x, then what she can do, she'll have a collection of these values of x, and she can take their average and use that as an estimate of the population parameter. Typically, we denote the population parameter for the mean to be mu, the Greek letter mu. You'll see that throughout the textbook as we go through the semester. Okay. Any questions about this problem here? Now, this is the worksheet that you're working on now, although you don't have your textbook yet. But I think the discussion we just had here kind of gives you a good idea of what we're talking about. And this will get clarified and amplified when you go ahead and open up your textbook and read about sampling in chapter 1. Okay. Any questions about number 1?
I guess my question would be kind of like identifying and differentiating the difference between like population and parameter, sampler and statistic. I guess like more of a, that's I guess a little confused about like the difference between.
All right, let's suppose, for example, that we want to estimate the proportion of registered voters that are going to vote for Proposition A in the next election. So we're going to do an opinion poll and query respondents, query eligible voters on whether they would vote yes or no, or they're undecided. So there are 3 possibilities there, okay? Now, let's suppose that our electorate is California. So we're looking only at California registered voters, and suppose our Proposition A is a federal-wide proposition, okay? Just imagine that all states will be voting on this proposition. Now, we're going to limit our sample, our collection of data from San Diego County only, okay? So what we've done is from that nationwide population of eligible voters who may vote yes, no, or undecided on Proposition A, we choose, because of time and resources, we choose to limit our sample to within San Diego County, okay? If we had more money and more time, we could amplify our sample, maybe to include Orange County or Los Angeles County as well, and try and get a good opinion poll for Southern California, okay? And there are some pollsters who might canvass the entire state. But now remember, the nation is voting on this proposition, so we're looking at a sample of data based on a local collection versus the national population of voters. Do you see that distinction there?
Yes.
Now, let's question this sampling method. California voters might have a bias, let's say, in their opinion. So when you look at sampling, you want to choose a sample that's unbiased. That is, there aren't any overriding factors that might move the proportion of voters one way or the other. We'd like to get a neutral, unbiased, unfiltered type of sample so that we get an answer that allows us to maybe extrapolate that sample mean to find out, or that sample proportion, and make a an assertion about the entire population, that's going to be tricky, isn't it? Because we've narrowed our sample to California, all right? So you can see that there are some real factors here that might influence our result. That is, if we want to say that if 51% of the voting populace is for this particular proposition, right, then we're going out on a limb. We're taking a finite sample, might be a large sample, it might be 1,000 registered voters in San Diego County. And what we're attempting to do is use that as an estimate of the population proportion of voters who would vote for Proposition A. And there are schemes for sampling that mitigate that potential bias, okay? Pollsters often use internet-based polls, and they will poll from a wide base of voters, trying to get voters from different economic and demographic regions, okay? Different economic situations, different demographic regions and factors. So sampling really wants to have a sample from which we can estimate the entire population mean or the entire population proportion. So when you delve into chapter 1, you'll see a number of situations. Now, can anyone tell me how you would, in the voting situation where we're trying to collect data from registered voters on their opinion of whether they're for or against Proposition A. And suppose that I have some resources and I can take a larger sample, or I don't have to restrict myself to San Diego County. Does anybody have any ideas on how to mitigate any biases that might arise when we narrow the demographic variable too much? How would we mitigate that? Can I call on somebody here? Cole, are you there? Cole?
Hello?
Yes. In this voting example that I just talked about, do you see the possibility of bias in the sample when you simply query San Diego County voters?
Yeah.
Okay. And how would you mitigate that bias if you had the resources?
Probably a bigger population size.
A bigger sample size, you mean? Remember, the population is this large and inclusive. It contains all the data set, okay? So in this particular case, the population would be registered voters across the nation, all 50 states. Now, here we are in San Diego, and we're trying to find out what the nation is thinking about this particular proposition. However, because of limited resources, our sample is restricted only to San Diego. Now, what if we had more resources? And I think what you were trying to say was that we could actually take a larger sample and maybe query other voters in other states to get a more unbiased, sample that would give us a better estimate of what the population proportion would be. So the population, again, is this large superset of all of the data, and the sample is only a subset, usually constrained by resources, time and money, in order to collect that data, right? So even with small samples, there are strategies by which we can reduce the bias in the sample and get a better estimate of the population parameter, which would be the proportion of all voters, of all registered voters on that particular proposition, right? Now, to go back to Cole's idea, what he might be thinking is, well, if I just have time and resources to collect 1,000 opinions, maybe here's what I'll do. I'll select 10 states across the nation from east to west, and I'll send them a mail questionnaire, or I'll set up an internet site where they can post their opinions. And what I'll do is I'll query maybe 100 people from 10 different states that I've selected across the country in order to reduce the bias by region, okay? Because we know that different regions might return different opinions on a particular proposition, okay? And of course, we have other divisions, we have parties, we have age groups. So there are many different stratifications that you'll see in the data. And then you'll devise a plan for your sample based on the amount of resources you have, the amount of time you have, and the tools that are available for you. Now, many websites provide tools for widespread sampling, okay? But the San Diego County example is not a bad example, because at least we'll get some idea of how the San Diego voters feel for this particular proposition. And if we now take a different population, somebody give me a different population for this problem, a smaller population. Can anybody think of a way that we can constrain our project here to a smaller population? What could we do there? Any ideas?
Maybe
Let's see,
the,
Cordell? Oh, go ahead. Yes, go ahead.
sorry.
Yeah, please go ahead.
Maybe the Escondido area, or like the like, you know, the certain mini divide districts in San Diego. You go for those areas.
Okay, I think what you're trying to say is that maybe if we take a population just based on cities in San Diego, and then sample from that particular population, you mentioned Escondido, and then here's what we do. We tell the readers of this opinion poll that this is how Escondido voters are thinking about this particular proposition. We don't purport to make any assertions about the entire population across the nation. We're simply looking at Escondido registered voters as our entire population, and then we select from that population some number of Escondido registered voters and so on, okay? So we've kind of narrowed our population. So you can see that one idea might be to look at a particular population based on certain demographics, and then of course your conclusions then would simply be about that population, the Escondido registered voter. So that's one way we could do this, okay? But again, if we're more ambitious and we'd like to see what the country is thinking about this proposition, then we'd have to use the entire population of registered voters in the country as our population. And then the challenge is to derive a sample that effectively, let's say, portrays or reflects the opinions of the whole country. So you can see the challenges in sampling, all right? And I hope that in this discussion, you have some idea of what a population is, which is the entire set of data, and then a sample from that entire population, which because of time and resources is much smaller. It might be orders of magnitude smaller than the number in the entire population. Okay, now let's look at number 2 here, and let me read the problem for you. Studies are often done by pharmaceutical companies to determine the effectiveness of a treatment program. Suppose that a new AIDS antibody drug is currently under study. It is given to patients once the AIDS symptoms have revealed themselves. Of interest are the statistics of the length of time in months patients live once starting the treatment. Now, in the early 80s, which was, more than 30 years ago, okay, AIDS had no cure. And so over the next 30 years, pharmaceutical companies have devoted lots of time and resources in a cure or even a vaccine to prevent AIDS. I don't believe it was ever discovered, okay? But certainly AIDS is not the threat that it was in the early 80s. So a lot of progress has been made in treating this illness. And of interest are the statistics of the length of time in months patients live once starting the treatment. Now, from number 1, we know that a statistic is based on a sample. The parameter is based on the population, right? So the population of AIDS patients, okay, has a certain mean length of time, okay, of survival, and of interest to the pharmaceutical company is based on this treatment. Can we lengthen the average time of survival for the patient? Okay, and so data has been collected on the following. Data has been collected from a sample, and what we've collected here are these numerical values which represent the months of survival once the treatment has started. And you can see that it ranges here. This data is listed in chronological or in numerical order, right? The minimum would be 2 months, and there's a maximum of 44 months. Now, how many observations are in the sample? Let's see, Kaylin, are you there?
Yes, I'm here.
Okay, what is
So,
the size of this sample? I have 2 columns here of the sample values. Do you see that? 2,
yes.
4, 11, and so on. And then the rest of it is over here in the 4th column.
Yep.
Okay. So how many samples have we collected in this study?
15.
Yes.
Is it 15?
Okay,
Okay.
8 here and 7 over here. So our sample size is 15. It's a fairly small sample, isn't it? And
Yes.
we're going to use statistics to derive information based on the sample about the population of all AIDS patients, right? And one thing that we can do here is take our sample of size 15 and calculate what we call the sample mean. And the sample mean is denoted by X bar. X is this variable that we talked about up here. Okay, and in this problem too, our variable is the number of months AIDS patients survive after starting the treatment. Okay, so we would add up the definition of the sample mean is to take the sum of all of the 15 values here and divide by the number, which would be 15. Okay, so StatCrunch, of course, will do this for us. We could also do this by hand. I could easily add up all of the values in this first column. Probably wouldn't attempt to do that without a calculator, all right, if I'm not using StatCrunch. So I can plug these into the calculator and add up all of these 15 values, get a sum, and then divide by 15, and that would give us an average. And we'll call that average X bar. Okay. And this is what you'll do on your first, some of you are working this out as we speak, okay? And what are these other columns? Well, the other columns are for the calculation of the sample variance, okay? And we'll define the sample variance later. I don't want to go through that yet, but let's focus in on the sample mean, okay? So if we would add these and go ahead and divide by 15, we would get an estimate of our sample mean, okay? We would get our sample mean, X bar, and that in turn would serve as our estimate of the population mean number of months AIDS patients survive once the treatment starts. And that would be useful to the pharmaceutical, okay? Because they would compare this treatment with other drugs that they have out in the market to see if there has been an improvement in the survival, in the length of the time patients survive, okay? Now, here's another variable based on the data, which we're calling a statistic. So X bar is a statistic. Mu would be the notation we would use for the population mean number of months. Down here, X tilde is a statistic, and it's based on the data. Now, how is X bar defined? We don't have our text yet, but I think you can grasp this concept. What we're going to do, rather than calculate the sample mean, we can calculate the median here, X tilde, as another estimate of the length of time patients would survive once the treatment is started. And what is the median? Well, median is the 50th percentile. The 50th percentile is the value for which there are an equal number above that value and an equal number below that value. Now, if the sample size is odd, the median is just the midpoint when you order the data from min to max. Now, this data happens to be ordered from min to max here, right? Okay, notice that the values are listed in ascending order from the minimum of 2 out to the maximum of 44, all right? Now, what would be the midpoint value of this data set, splitting the data right in half, okay? Well, since there are 15 values that in the sample and they're ordered in ascending order here, all we have to do is take the middle value, which is the 8th value in the data set, right? The 8th value in the data set has exactly 7 values which are bigger than it and 7 values which are less than or equal to it, okay? And here we have 16. as our median here. Okay, why 16? Well, because it's the middle value, 1, 2, 3, 4, 5, 6, 7, 8. And here you see exactly 7 values, which are less than or equal to 16, and then 7 values, which are greater than 16, okay? Now, here's another example of data. Let's take all of the sales prices in North County, San Diego. So I can go to realtor.com, and on that website, they will show me all the sales prices, let's say in the last 6 months, for homes sold in North County, San Diego. And I can analyze that data. I can derive a sample of that data, and I can calculate the sample mean of that sample and the sample median, x tilde, okay? Now, the reason that we might look at both of these statistics at the same time is the preponderance or the possibility of outliers. An outlier is an observation in your data set which may be much larger, okay, than the mean, okay, or much smaller. Suppose we had a value in this list that was grossly bigger than these values here, something like 102 months. So if I type in 102 here and take the average to try and estimate the population mean, okay, it would be skewed by that outlier of 102 months, wouldn't it? Because what are we doing in the mean, in the sample mean? We are adding values. So if we add 102 to the sum, we might skew the data a little bit, okay? But the median doesn't take into consideration the numerical size of the values. All it does is take the order, and it takes the middle value in that ordered list and gives you that estimate as the number of months of survival after the treatment starts, okay? Or in the real estate example, there might be a home in a very expensive area, high sales. I was reading the other day that in Los Angeles, there was a property, I think it was owned by Jeffrey Katzenberg, and the sale price was $65 million. Okay, now even though LA County has a lot of expensive homes, that one in particular stands out as an outlier. And if a new buyer went into Los Angeles and said, well, I want to know what the average home price is, the realtor would say, no, I won't give you the average because we had a sale last month that skewed the average. What I'll do is I'll give you the median, okay? The median is not affected by that one large outlier because it doesn't take into account the numerical value. It only takes into account the fact that it may be the max, right? It'll still take you the middle value, okay? So there are some benefits in looking at a variety of statistics when we want to describe, let's say, the center of the data or the typical value of the data set. A new buyer comes into Los Angeles and says, what is my investment going to be? How can I understand what the home prices are? And if I look at the median value, it might give me a better idea of how to make my investment, okay? Okay, I think I'll stop there with number 2. And again, I won't define the variance at this point. So we won't get into a discussion of the variance yet. Now, here is another way that you can try and understand your data. The data is numerical, as I said, and here is the video game example. And so researchers are looking at the number of hours of video games played by school-aged children and young adults. They each randomly sampled different groups of 150 students from the same school and collected the data displayed in the table below. Okay. Now, the school might be a middle school, and it might be a high school, so we don't know. We just know that 150 students have been sampled from the same school. And what we've done is we have created a way of binning the data. What we're going to do is define non-contiguous classes here, representing the number of hours played per week by the 150 students. Some students don't play very often, and maybe the variable, that is the number of hours played during, let's see, gathering hours, and there's going to be possibly a time window here. So some students may only view video games, let's say between 0 and 2 hours, others strictly between 2 and 4, and so on. Now, what we can do is bin the data, and so we'll look at those 150 numerical values, and notice that we have a max here of 12. Okay, so we define our range of values to be between 0 and 12, and those 150 values then are all between 0 and 12 hours. And depending on what the value is, we will count up the number of values in a particular class. And here you see the frequency. So the frequency is the number of values in the sample of 150 students that viewed video games between 0 and 2 hours. Now, how many in the sample viewed video games more than 2 hours up to 4 hours? Well, according to our frequency table here, 30 of the 150 students actually viewed video games between 2 and 4 hours, okay? And so on, okay? Between 6 and 8, it's 25, according to the table. Between 8 and 10, it's 12. And between 10 and 12, it's 8. So what the researcher has done, he has collected 150 data values here, representing this amount of time in hours, okay? And he's binned the data based on these pre-assigned classes here. So he has chosen these 6 classes, and he's going to divide up the data into these 6 classes, the distribution of the data. Okay, so he's counted 26 in the first class, 30 in the second class, and so on. Now, here's a blank right here. And we're going to figure out what that blank contains here. And here's how we're going to do it. Now, if we add up all of the frequencies in all of the classes here, what should the number be? Okay. Let's see. Let me call on Vivica. Vivica, are you there?
Yeah, I'm here. I'm still calculating it. I'm still doing it.
Are you okay? Okay.
Yeah.
So the question was, Vivica, what should the second column add up to? Remember, we're sampling 150 students, and we've binned their response in terms of the number of hours they played. Okay, you see how we got the 26? The 26 because 26 of the students said they played between 0 and 2 hours, right?
Right.
Okay. So what should this second column add up to here?
90? 90?
Well, we've got a blank here, don't we? Right?
Yeah.
Okay, so let's see, you added up 26 and 30, that's 56. 56 and 25 is 81. 89. Okay, and 89 and 12. 89 and 12 is 101. Okay, so that's 101. So what should this blank frequency be here? If these other 49, good. Okay, because the total column here adds up to 150. So on your worksheet, you're going to, add up these 5 numbers, get your 101, and then subtract it from the sample size, and that tells us that in this particular class between 4 and 6, there were 49 that responded between 4 and 6 hours. Good. Okay. Now, Vivica, can I keep you on the hot seat here?
Sure.
Okay. Now, what would be the percentage in this second class? Remember, there were 30 out of 150 that responded, they played between 2 and 4 hours. So what is the frequency of this class here between 2 and 4?
30?
Yes. And then the relative frequency would be what?
0.20. So 20%, right?
And how did you derive that? You
Um,
took the 30
and then
and you divided
you divide it by 150, and that gives you.
you divided by 150, right? And so that gave us a relative frequency 30 over 150, which would be 0.20. You see that? Okay.
Yeah.
Now, how would you fill in this blank here? This first blank on top.
You would divide 26 and 150, and then whatever you get is your relative frequency.
That's right. And just for fun here, let's take out our calculators and divide 26 divided by 150, and we get 0.173333. And we could round that to 3 places as 0.173. Okay. Now, so we could easily calculate the relative frequency for the first class as 0.173. And what about this third class? We said that the frequency was 49. So now if we divide 49 by 150, we'd get something very close to 1/3. Okay. And in fact, if you round that to 3 places, 49 divided by 150 is equal to 0.327 if we round it to 3 places. Okay, so we could easily fill out this third column here by dividing the frequency by the sample size to get the relative frequency. And Vivica, one last question. What do these 6 numbers, these 6 relative frequencies in the third column, what do they add up to?
I haven't finished doing all of them yet. I'm almost done.
Well, don't do any
be
more
one.
calculation. Yeah, it should be
Oh.
1, shouldn't it? Because remember, the denominator here for our fraction is 150. All of these 6 numbers add up to 150. So all of the relative frequencies should add up to 1, or very close to 1, depending upon your rounding. Okay? All right. So convince yourselves that when you divide by 150 and get the relative frequency, that the sum of your relative frequencies will be equal to 1. All right? That's just another way of saying that these 6 frequencies add up to 150, right? Okay. All right. I think we'll stop it there, and we can continue this discussion next time. It's a little unfair to ask you to solve these on your feet here because we don't have our text yet, and I haven't given you the information. I just described it for you. I think maybe on Tuesday, what I'll do, and this is a big no-no for instructors, but what I might do is show you the slides, and maybe we'll go through some of those slides just as a fallback, because most of you haven't acquired your text yet. And I'll post those slides this weekend or maybe even tomorrow. And then on Tuesday, we'll go over it. And then what we've discussed here today will make a lot more sense to you after you read those slides, okay? All right. Okay, any questions about these problems, these first 3 problems that we've done?
What decimal place do you want us to round to?
Most of our examples, we can get away with no more than 2 or 3 decimal places. I did mention that when you add up your relative frequencies, you'll get a number here that may not be equal to 1. Okay, it just depends on how you round here. So if you round to 2 or 3 decimal places, in most cases you should be good. Okay, and if I see a sum here of 0.991 or 1.003, I'll give you full credit because I know that there might be some inaccuracy resulting from rounding. Okay, but this number here, by the way, this value here or this notation here is the usual notation that you'll see in statistics textbooks for the sum. And in most mathematics courses, you'll see this, this notation here. It's the Greek letter sigma, okay? And sigma is typically used to denote sum in mathematics. So when I have a sigma here, it means the sum of all these values here, okay? So to go back to the rounding question, round your values to 2 or 3 decimal places unless you're instructed otherwise, all right? So if there aren't any instructions, you can round to 2 or 3 places. If the data are whole numbers, then you don't have to deal with rounding, okay? Although when you take the mean, you might have to round there, even though you started with whole numbers. We'll do a lot of examples and you'll see how that works out, okay? All right. Any other questions about these first 3 problems?
On the second question, you were talking about how if there was
The show dog.
what was that?
Talking about what
You're
now?
talking about how if there was a like extraneous value, like at the end, if there was like a 102.
Outliers, yes.
So you were saying not to disregard that value, but just to switch your perspective, like the mean or median.
Yes, and that perspective depends on what the data is, okay? And many times, if there are going to be datas that are far away from the mean, the sample mean, okay, then those might be considered outliers. Now, then there's the question, and I think you actually touched on this a little bit. Do you keep that in the data set or do you trim the data set of those outliers? That's a sensitive question because in in the computer example that somebody talked about last Tuesday, there might be situations where these outliers can be deleted, or they can be disregarded and omitted from the data set, because in testing electronic devices, sometimes there might be electrical anomalies in testing the device in terms of its duration. And so engineers might know that there are certain effects that would skew the data, and they would justify the exclusion of those data points as physically caused by anomalies. And in the real estate case, you know,